Okay, partial pressures. So partial pressures involve another set of ideas that were developed by our good friend John Dalton. And John Dalton, when he was doing all of his work around atoms, some of the work he did actually led him to this idea. So this image here, we've got three different gases. We have gas A with its little particles, right? And we have gas B with its particles. And we have gas C with its particles. So you have to remember that when we're talking about pressure, pressure depends on collisions, not on the identity of the substance. So in general, what that really means is that what we are looking at is total number of particles is what's going to contribute to the overall pressure, as well as how hard those particles are colliding, but really we're focused on the total number. So you're going to have some amount of pressure that comes from all of the collisions going on for A. You're going to have some pressure coming on from all of the collisions with B, and you're going to have some pressure that is occurring because all of the collisions going on in these particles C. So if you combine them all, what that means is you have more particles. And if you have more particles, that means you have more collisions. And if you have more collisions, what you have is more pressure. So you can take all of these little A particles and you can shove them into this box, right? We'll shove them all together. And you can take all of those B particles and you can shove them all together in this spot, and all of the C particles. So now you have more particles than you had before, and all you have to do is simply add up the individual particles or the individual pressures to get an overall pressure. So this is really nice because it's one of the few places where we get to just look at addition. So if there's addition, however, that also means there can be subtraction, because if you have the total pressure and you need one of the individual pressures, you just have to subtract everything else. So let's look and see what a simple problem like this would be. Okay, so it says when a certain amount of nitrogen is introduced into a 1 liter flask already containing oxygen, the pressure in the flask increases from 35 to 77. Calculate the partial pressure of each gas in the final mixture. Okay, so it can actually be helpful to have a diagram. So here I've got a flask, it's 1 liter. And in that flask, it's already containing oxygen, right? So I'll say oxygen is diatomic, so I've got little oxygens. Okay. And I'm going to add, right? Introduce means to add nitrogen. So let me do another thing here that is saying adding nitrogen. So I had my oxygens, and now I am adding nitrogens. So now I have more stuff in here. Okay, so that's what this process is describing. And then it said it went from 35 kilopascals to 77 kilopascals. What's the partial pressure of each gas in the final mixture? So I went from 35 up to 77. Well, what was the 35 and what was the 77? The 77 is a mixture of oxygen and nitrogen. The 35 is simply only oxygen because that's all that is in that container. So my pressure of oxygen is equal to 35 kilopascals because that was what was initially in the container. So that has to be only the oxygen. So the nitrogen has to be the 77, the new pressure, minus the 35, which was the original pressure, and that gives you 42. So the pressure of the nitrogen had to be 42 kilopascals. And just to double check yourself, you can make sure that if you add those two together, you're going to get 77, which is what it said was in the final mixture. But my answers are right there. Okay, collecting a gas over water. This is essentially the most standard lab technique with gases. And we are going to do this lab technique. We'll pull out some big buckets and some other containers and some flexible tubing, and we're going to do some stuff. So, pretty much the only way that you can guarantee that you only have the gas you want and not air, all right? So collecting a gas over water prevents mixing with air, which is important because air is actually a really messy mixture of all sorts of other gases, and I don't want to deal with it. But if I am collecting gas over water, what I am going to have is tiny little bits of water molecules in here because I do have some water vapor. So what you need to realize is that the total pressure, right, P total, inside that container is always going to be some amount of water vapor plus the gas you actually want. So here's how these lab setups are typically going to happen. You are going to be given or determine that total pressure. The pressure of the water you look up in tables, and it's based on the temperature, which means to get the pressure of the gas, which is what these questions are always wanting, you subtract. Okay, you're going to subtract the total pressure and the water vapor, and that's going to tell you what the pressure of the remaining gas inside the container is. So let's do a problem. Okay, so it says a student performs an experiment in which she prepares hydrogen gas by reacting zinc metal with hydrochloric acid. After collecting 250 milliliters, that's a volume, of the gas by water displacement, which is what I just showed you, the student equilibrates the system to an atmospheric pressure of 99.2 kilopascals. So that's my pressure. And the lab temperature of 24 degrees Celsius. That's my temperature. Given that the vapor pressure of water is 2.98 kilopascals at 24 degrees, what mass of hydrogen has she collected? Okay, so what do I see here? I see a volume, I see a pressure, I see a temperature, I see another pressure, but this pressure is of water. So that means this pressure, this 99.2, that must be a total pressure, and this is the pressure of water. So my total pressure, again, is the pressure of water plus my pressure of gas, and my gas here is hydrogen. So let's plug some numbers in and actually get that answer. So 99.2 kilopascals is equal to 2.98 kilopascals plus the pressure of hydrogen. So that's just a subtraction. So the pressure of hydrogen, if I subtract out those two things, I'm going to get a nice answer of 96.2, actually just 0.2 because of my sig figs, kilopascals. So now that's a pressure. So I have a pressure, I have a temperature, but I can't do anything with that temperature because it's in Celsius. So my temperature has got to be 24 degrees Celsius plus 273, which is going to be 297 Kelvin. So now I have a pressure, I have a temperature, I have a volume of 250 milliliters, and it's asking me for mass. Well, I don't have any formula that has mass, but I do have a formula that includes pressure and temperature and volume, and that is PV, PV equals nRT. So how can I get mass out of this? Which of those variables is related to mass? Well, it's my moles here. My N I can convert to mass using the molar mass. So I need to get N. So rearranging my formula for N is going to give me P times V over R times T. Great. So open a parentheses. That pressure was 96.2. The volume was 250.0 milliliters. Guess what? I can't use milliliters in PervNerd. I have to use liters. So if you'll remember from Chem 1, that means my decimal is going to move over 3 times, so 0.2500, close parentheses, divided by R. I need the R value for kPa, and that is 8.31. And again, you're not memorizing that. It's in section 8.2, and it will be on the AP formula sheet. Times my temperature, 297. So that's going to give me a mole amount, and I'm going to take that to 3 significant figures. So do all that in the calculator, and I should get 0.00975 moles of hydrogen. But I don't want moles. I want grams. It's asking for mass. So I've got moles. So I need to divide by mole, and I need to multiply by grams of hydrogen, which is the molar mass, 2.02. So when I calculate that, and again go to 3 significant figures, that is going to be, plug that in, 0.00975 times 2.02. And it's going to give me 0.0197 grams of H2. Again, 3 sig figs because all of these things have 3 sig figs. Okay, so another way to look at partial pressures is this thing called a mole fraction. So to explain a mole fraction, I want to talk about percentages. So partial pressure, when you see the word partial, that involves part. And when we're talking about percentages, remember that a percent, any percent, is simply a part over a whole. So a partial pressure really is simply the part of my gas over my total gas, right? That's all it is. Well, another way to do that would be to think, so the P total would be, say, the pressure of oxygen, right? Or the percentage of oxygen that exists, right? So the percent of oxygen times the P total, right? Plus the percent, say, of nitrogen times the P total, that sort of thing. Well, we don't deal with percentages. We deal with fractions instead because it's a little bit easier. So this mole fraction is simply a part over a whole. The whole is your total number of moles. So that is your, oops, not that. Your whole here, that's your total number of moles. And your part is the moles of just one thing. So what you can then do is say that the pressure of some substance, so we'll say the pressure of oxygen, is equal to the total pressure times actually this mole fraction. And you just need to remember that the mole fraction is the part of the thing you want over the total amount of moles. So what you're normally going to have to do is calculate moles, because we're not normally going to give you moles, we're normally going to give you grams, which you will have to convert to moles because that's all you can do. And then once you convert it to moles, then you can calculate your mole fraction. And then this is simply a multiplication of the mole fraction times the total. So as an example, a technician injects 7.50 grams of liquid nitrogen. And remember, nitrogen is a diatomic, so it's N2, into a sealed glass bulb filled with 12 grams of neon. Neon is simply just Ne. The nitrogen vaporizes and fills the container to produce a total pressure of 1.4. All right, so my P total is 1.40 atm. What is the partial pressure of each of the gases? So I've got a total pressure. I don't have another pressure. So how do I know I need mole fractions? Well, because I have grams I can convert to moles, but I only have one pressure here. If I only have one pressure, then I can't do any addition, subtraction things. It just doesn't work. So I need to deal with this nitrogen and this neon. So first off, nitrogen, let's start there. So 7.50 grams of nitrogen. What is the only thing you can do with grams? You have to convert it to moles. How do you do that? Using the molar mass. So N2, each nitrogen is 14.01, so two of them together is 28.02. And I'm going to divide those two things. It's going to give me three significant figures, so 0.268 moles of N2. And then I'm going to do the same thing for the neon. 12.0 grams neon. The only thing I can do with mass is convert to moles. Neon is not a diatomic, so I don't need to worry about that. Neon is 20, double check here, 20.02, I believe. I think that's right. And then once I divide those two things, again to three significant figures, mole of neon. Oops, my bad. The 20, that's 20.18. Okay, 20.18. Let me just double check that math. 20.18. 0.595. Okay, great. Okay, so those are my individual moles. So what are my total moles? Well, I have to add those two things together. So 0.268 plus 0.595 is going to give me a total of 0.863 moles total. So how am I going to calculate these things? Well, the pressure of nitrogen is going to equal the total pressure times my moles nitrogen over my total moles. So what does that actually look like? Well, it's going to look like 1.40 times 0.863 down here, 0.268 up here, and do that in the calculator. So 1.40 times 0.268 divided by 0.863, stick with 3 sig figs, and I get 0.435 atmospheres. That's my nitrogen. Switching over to my neon, it's the same thing, right? My pressure of neon is going to be equal to my P total, which is 1.40, my 0.863 in the denominator, my 0.595 in the numerator. Do that in the calculator. 1.40 times 0.595 divided by 0.863, and that should give me 3 sig figs 965 atmospheres. Now, just to double check yourself, while you're still getting used to these problems, I suggest you add these things back together and make sure they equal the total. And sure enough, 0.435 plus 0.965 does equal 1.4.